Hello, everyone. Welcome back. Today, we're going to be talking about ether cleavages and epoxide openings. So, we're going to start with the ether cleavages side of things by taking a look at a traditional ether, right? So, your functional groups would lead you to say an ether is an oxygen that's connected to two different carbons, right? And one thing that's true about these guys is that they are highly unreactive, right? And the reason for this comes from the fact that there's not much they can do. Right? There's not really a good leaving group. There's not really much going on. And so, since this is usually a bad leaving group and CO bonds are strong, usually we say these aren't going to do much. But the thing is, let's say you took this diethyl ether and you threw it in to a reaction with hydrobromic acid, just one equivalent, in water at reflux. What you would see is that you'd actually form ethanol and ethyl bromide. So the question is, why does this specific reaction happen? And as a matter of fact, it's just a fancy version of SN2. All right. So first thing we need to do, though, in order to understand this fancy version of SN2, is we need to talk about something that we haven't talked about yet, but it's actually very important for a lot of the mechanisms that we're going to look at in organic chemistry. And that is what is called the leveling effect. Now, this is something that you likely talked about in Gen Chem, but you probably forgot about it. Essentially, what the leveling effect is the strength of an acid is equivalent to the conjugate acid of the solvent, right? And this is because acid base with the solvent happens first. So here's how you should think about this, right? Imagine you have a beaker that is just full of water and then some of that ether that we were looking at beforehand. Right, woo, here we go. So there's a bunch of H2O just hanging out in here, right? And since there's so much H2O hanging out and there's so little ether, that when you actually take a drop of the HBr, right, so say this is hydrobromic acid, and you put it in there, what's going to happen is before this even reaches the ether, there is a favorable acid-base reaction that can happen where your H2O and HBr interact, right? And clearly, what we normally see with water and a strong acid is that you'll make H3O plus and Br minus. All right, and this happens practically immediately, right? Remember what we said in the last lecture regarding acid-base chemistry is one of the fastest reactions that you can do. So essentially, what we're saying is anytime you put a strong acid in solution, this is usually the first result. So with that in mind, let's think about the ways we could actually do this type of reaction. Right? Let's look at what could be a mechanism. So the first thing that may come to mind is, okay, well, we have in the end of this, we're substituting out a bromide, right? So wouldn't it make the most sense if we had this Br minus come around, just do a backside attack and kick out that oxygen? But this doesn't make much sense, right? Think about it. If we do this, we would generally be making an O minus with the ethyl bromide. But if we're comparing Br minus and O minus, we are going towards a more unstable product, right? So this just isn't possible, okay? We would generally say that something like this, which is just our traditional SN2, can't happen, right? It just energetically makes no sense. So instead, something different has to occur. All right, so let's think about what's actually happening in the solution. Well, first things first, if our H2O and HBr are coming into contact with one another, which we know they are, the first thing that's going to occur is we're going to generate H3O plus and Br minus, right? And we'll actually draw out the bonds of this H3O plus because we are going to need to for what happens in just a second. So this H3O plus is a strong acid, right? Which means that when this ether comes around and finds it, which will happen over some time, it can do a favorable acid-base reaction. It's essentially equilibrium is 50-50. So upon doing so, we now have this positively charged oxygen. This is now a good leaving group, right? Because upon our bromide coming in and doing a backside attack, what we'll see happen is we've kicked out a neutral oxygen. So we go from two charged species to having these two neutral species. Okay? So, what does this look like energetically? We're going to once again use BDEs to talk about this reaction because this is essentially an SN2 reaction that's done in a weird way. And as a reminder, Br minus is a strong nucleophile, but it is a bad base. So it's not like we're ever going to see E2. We're only going to see it do some SN2 reactions here. So looking at our energy, for step one, right? Our bonds broken are, and this is of course the acid base that we're talking about for step one. Our bonds broken are the HBr bond, and then our bond formed, we are forming the OH bond. Right? What this comes out to be is that HBr bond is 88 kcals per mole, and then the OH bond is 119 kcals per mole. So overall, our delta H for step one is negative 31 kcals per mole. This is pretty expected, right? Because as we said before, this was going to be a favorable acid-base reaction, and it is. So now if we look at step two, right, we have, in this case, we are forming an OH and we are breaking an OH, right? So our broken bonds is an OH, and then our formed bonds is an OH. This is why I said the equilibrium should be spot on because these just cancel each other out. Then if we look at step three, right, we'll draw that down here so that we're still close to our reaction. We are breaking the carbon-oxygen bond and forming the carbon-bromine bond. All right, and as a note for this one, these are primary bonds. So it is a primary carbon-oxygen broken, and then formed is a primary carbon bromine bond. And so the carbon oxygen bond is actually much more energetically stable, which is why these are so hard to react in the first place at 91 kcals per mole, whereas the primary carbon bromine bond is 68 kcals per mole. Right? So the delta H for step three ends up being positive 23 kilocalories per mole. And what this ends up doing is if you add all of these together, we find that our delta H reaction is actually negative 8 kilocalories per mole. So it is favored, right? It is overall favored. But if we look at this in an energy diagram, it's an interesting story, right? So let's say we draw this out, energy over the reaction. So here's our reaction progress. Here's our energy. So we start out with something that is high in energy, right? HBr is one of our reactants. So if this is reacting with our H2O, we know that step one, we just talked about it, acid base is really low in terms of its activation energy, but it goes down pretty far, right? Because we end up with that H3O plus and the Br minus, which is much more stable. And as a matter of fact, this is one of the values that we just calculated. From here, this then does that step two, which is the acid-base proton exchange between that and the ether, right? So now we have our ether with the positive charge. Then the final step is very difficult to do, right? Think about it. It is an SN2 reaction, right? And so it's going to be a high activation energy step. And then we're also doing it's endothermic, right? Delta H3 is plus 23 kcals per mole. So it takes a lot to get to this product. Sorry, the product is actually drawn a little too high because it should be down here. But essentially, what we see is the overall course of the reaction, right? We see that the delta H of the overall reaction is -8 kilocalories per mole. But the delta H of that last step right there is plus 23 kcals per mole. So essentially, we put ourselves into a 31 kilocalorie trough by doing the first acid-base reaction that we then have to make up later on. And that's why when we're looking at this reaction, the SN2 right here is actually our rate determining step, right? It is very difficult to perform. So what does that actually mean for our reaction, right? What it means is that we have a very high activation energy right here that we need to get over. So anytime we have a very high activation energy, we need a large amount of heat, right? Because it's technically an endothermic step to get to the product. Now, that being said, the entire reaction is exothermic, so it's still favorable. You just need heat to make it happen, right? So essentially, all of these have to be done under reflux, all right? But overall, still a relatively favorable reaction. Now, that being said, if we look at our original scheme up here, right? Where was it? It was right here. We said that there's the reflux, right? So that's what we need for the heat for this to go. But we only used one equivalent here. What happens if we use multiple? Well, essentially, excess acid means more cleavages. Because notice that after one equivalent of the acid, we ended up with an alcohol on one thing and then the alkyl bromide for the other. But what if we did excess? Well, in the case of excess, we would actually end up with two ethyl bromides. And the reason for this is because it essentially just does the reaction twice, right? If you add one equivalent of the HBr at first and water at reflux, you would end up forming, once again, that ethanol and the ethyl bromide. But then another equivalent of HBr is going to then do the same exact thing, right? Where essentially we have the alcohol and then we have our H3O plus, because remember this is made very quickly upon entering the solution. We'll protonate that alcohol to make it the OH2 plus. And at this point, the bromide can then come in and do a backside attack, kicking that out and leaving us with another ethyl bromide. So essentially what we're looking at here is the more acid you have, the more times you can substitute it. All right. The other thing is that stronger acids react faster. Okay. So thinking about this idea, there are multiple reasons for this. So if we look at this same reaction and we look at it in terms of using HI, right? And let's say we're doing all of these with one equivalent. So if we did HI, instead of forming the ethyl bromide, we would form ethyl iodide. If we did HBr, like we just saw, we're going to form the ethyl bromide. And then HCl is going to form the ethyl chloride. But in each of these, the bond dissociation energies are going to be a little different. right? As a matter of fact, the chlorine is going to form much stronger bonds. But the issue is the HCl bond is also stronger due to it being a weaker acid compared to something like HI. And so what we end up with is we end up with a differential of the delta H's of reaction, where up top, the delta H reaction is negative 10 kilocalories per mole. For HBr, we already saw it is negative 8 kilocalories per mole. And funny enough, chlorine keeps the trend going, where it also differs by 2, where the delta H reaction is negative 6 kilocalories per mole. But the important thing is they're also faster because if you think about it, this iodide is going to have the lowest activation energy because I minus is the best nucleophile here in water. Right? Those solvent effects come back into play where we talked about it's harder to solvate the iodide, so it's a better nucleophile, right? Versus the Cl minus is the worst nucleophile in water. Thus, this has the highest activation energy. So if you ever want to run this reaction, you would want to use something like uh, hydrogen iodide as your acid source because it's going to react the fastest. Okay? Now then, looking a little further than this, we've been looking at all these where these carbons have all been primary. But what if they were not? Right? Let's say that we were looking at substituted carbons that are a bit more bulky. Right? Say we were looking at something that was a couple tertiary carbons. Well, in this case, if we were to toss in HBr, let's say in excess, water and some heat, you would expect that if this were operant by an SN2 mechanism, no reaction would occur. But surprisingly, what we see is that this once again generates two alkyl bromides. So why is this? Well, if we take a look at the mechanism, we would see that the first thing that happens is still the exact same thing as the first thing that happens in the other mechanisms, right? We start out where we've made H3O plus between the HBr and the water. And then from here, our ether is going to take the proton, right? It's going to become a protonated ether to make that a good leaving group, oxygen. And now we're sitting here on these tertiary carbons, which we know can't do SN2, right? So if we can't do SN2, nothing will happen. Now, that being said, remember that nothing would happen in terms of SN2, but that doesn't mean nothing can happen. Think about it. We have a good leaving group on a tertiary carbon. It can leave on its own, right? So nothing will happen until SN1. Because from here, this leaving group can just leave. Upon leaving, it frees up a tertiary carbocation. And with this, now our bromide, which was just chilling out and couldn't do anything before, can now come in and add. And as a reminder, bromide is a very bad base. So even though it has that negative charge, it actually still won't do elimination. It will only substitute on. And then the leftover other part of this, which is that tertiary alcohol, it can just do it again, right? Because from here, we have generated one equivalent of the tertiary bromide, but with that excess acid, right, this guy is still reactive. So because of that, it will then go through and do the same substitution. So essentially what we're saying is tertiary carbons or tertiary ethers go through SN1. Okay? But that leaves the question, what about secondaries? Well, this question's actually a really good one because the answer is nobody really knows, right? You only know after you do the experiment for it. Because let's say we tossed in this diisopropyl ether with some HBr excess and H2O and heat. It does still make two of the secondary alkyl bromides, but it could be SN2 or SN1. It's actually a mix, right? So it just proceeds through both of these mechanisms however it wants to, right? Because of that, we're not going to focus on these secondary leaving groups because they don't make as much of a difference. Okay? So, with that being said, just keep that in mind when we're thinking about these types of reactions. Now, that being said, there is another type of ether cleavage that we can see, right? All of these that we were looking at were with these acids up here, the hydrohalogenated acids. So it's essentially just hydrogen with some type of halogen, Hi, HBr, HCl. But there is other types of strong acids, right? Think about a reaction with sulfuric acid. Right? We can imagine that this is going to actually act a little differently. So let's take that same tertiary ether that we had before, and this time let's add in H2SO4, H2O, and a bunch of heat. Right? And we don't even have to list equivalents here because it's going to give us something interesting. So what we'll see is that it's going to generate two tertiary alcohols. So how does this happen? Well, mechanistically, it's going to work the exact same as everything else, right? Where from the start, we have H2SO4 hanging out in our solution with water, right? The H2SO4 is going to protonate our water first off, which is then going to give us the H3O plus, which we already knew would happen due to the leveling effect. But here's the thing. Unlike the other um, acids that we've been looking at right now, H2SO4's conjugate base is a little different because even though it has a negative charge, it's shared amongst three different oxygens on the sulfur. And what that means is that this structure right here is an awful nucleophile, right? I won't even just say bad, I'll say awful. It is both an awful nucleophile and base. It is essentially a spectator ion. You won't see it do anything in terms of reactions. It will just exist as a spectator in the reactions. So what does that mean for us? Well, what that means is that now whenever our ether gets protonated, right? So let's say this tertiary ether then meets with that H3O plus and it gets protonated. It will now have a good leaving group. And once again, like the other cases where this became a good leaving group, since it's tertiary, it has to undergo SN1. So the leaving group itself will leave, and we'll end up with a carbocation as well as one of our tertiary alcohols. But if this now a HSO4 minus, which is practically a spectator ion, it's not a good enough nucleophile to do anything. So what is a good enough nucleophile to do anything? Well, it would have to be water, right? Water is the only okay nucleophile in solution. And since we have acid in the solution, this can't even act as a base because the pH is so low. So instead, what it's going to do is the only thing it can do, which is it's going to do an SN1 like normal. right? So the H2O is going to add in there, now make that tertiary carbon-oxygen bond, which more water can then come in and pluck off one of those protons to keep the solution acidic. And that's where we get our other tertiary alcohol from. So sulfuric acid is relatively neat because it goes through and it actually does these mechanisms, but it uses water or whatever the solvent is, usually as the nucleophile to replace with. Okay? Now then, that being said, there's one other thing that we need to keep in mind with these ethers, and that is not all ethers are cleavable, right? Take, for example, something that looks like this. So, if we were to toss this in with excess HBr under reflux, what we would see is rather than the ether getting cleaved into two alkyl bromides, the oxygen stays on one side and the alkyl bromide exists on the other. So the question is why? Well, think about it. We have, in this case, a primary carbon, right? So really good for SN2. But then this one right here is an sp2 hybridized carbon, right? And as we know from our previous lectures, this can't substitute. And because of that, whenever this goes through this reaction, essentially this bond will never be broken because it just can't do a substitution. So what that brings us to is a quick summary of ether cleavages. Because we essentially have four different types of ethers to consider, right? If it is a primary ether, it is SN2 only. If it is a secondary ether, it is SN1 slash SN2 mix. If it's a tertiary ether, it's SN1 only. But then finally, if it's an sp2 hybridized ether, there will be no cleavage on that side of the bond. Okay? So those are things to keep in mind when we're looking at these ether cleavages. Essentially, though, keep in mind these are just SN1 and SN2. The only difference being you have to protonate something first. All right, so that's why we're talking about these at this point because they're the exact same as the reactions we've been talking about so far. Now then, on to the second part of our lecture, right? And that is epoxide ring openings. So these ring openings are really interesting because we were talking about last time the formation of rings. Now we're going to talk about the opposite, which is breaking rings. And so the way this sort of reaction works is you can imagine if we were to take something like this epoxide here, right? Which an epoxide, if you remember your functional group handout, is just a three-membered ring with an oxygen in it. Essentially, what we're going to see is upon addition of hydroxide, right? So something like NaOH, and this could be in water at 100 degrees Celsius, make it really hot. What will happen is this will break apart and we'll actually end up with two alcohols. So the question is, how does this happen? Well, let's take a look at a mechanism. In the case of this reaction, we would see that the hydroxide would come in, act as a nucleophile, and actually do a backside attack and kick out that oxygen. Now you may be thinking to yourself, why would this be okay? Well, in this case, the reason has to do with something that we'll talk about in just a second. Because normally we'd say an O minus is a really bad leaving group, right? Well, let's take a look at what would happen after this. Essentially, we would say that the water that's in solution would then have to act as an acid, where this O minus would be our base that could come around, grab a proton, and that's what makes it an alcohol in the end. Now, thinking about this reaction, it theoretically should be 0 kcals per mole. Because think about it. In step one, what we're breaking is a carbon-oxygen bond, and what we're forming is a carbon-oxygen bond, right? So these just cancel. And then in the second step, what we're breaking is a hydrogen-oxygen bond, and what we're forming is a hydrogen-oxygen bond. So this should also cancel out. So we would say that delta H of the reaction should be 0, but the delta H of the reaction experimentally is negative 13 kilocalories per mole. So the question is how, right? Think about it. It's the other reason that this reaction even works in the first place. When we look at that original starting compound, it has a three-membered ring in it. And as we talked about in the last lecture, the smaller the ring, the higher the ring strain. And we said that the ring strain on this molecule in particular was 13 kilocalories per mole. You can imagine this as like a loaded spring, right? That's ready to just release energy. Because upon reaching the products, it shouldn't be hard to see, but these have a ring strain of 0 kcals per mole. So where does that energy go? Well, the energy is being released, right? That 13 kcals per mole going to 0 is just releasing it. So if this is being released, it must be exothermic, right? And thus our delta H is negative 13 kilocalories per mole. So what this looks like in our energy diagram, and the reason this reaction works in the first place, is that overall energy over the reaction progress occurs within the first step, right? Going from those reactants, which have that three-membered ring, it goes up and then down across this negative 13 kcal per mole delta H, right? Because the second step after reaching this intermediate is just that simple acid base, which should be completely the same, just with a little bit of activation energy. And so when we're looking at epoxide ring openings, this first step where we're kicking out a bad leaving group is okay because we're getting a ton of energy from the ring strain, right? So kicking out bad leaving group, okay, due to ring strain released. And the thing is, you need to be mindful of the fact that a lot of this ring strain release does not apply to other rings. If you look at something like a five-membered ring, that has 5 kilocalories per mole of ring strain, but it doesn't crack open like this because there's not enough strain for it to want to. All right. This is very specific to epoxides. Okay. And so these epoxide ring opening reactions can happen in the way that we've shown up here above, or they can happen a second way. All right, so we're going to classify these into two ways to open epoxides, right? The first one is basic epoxide ring openings, and these use a strong nucleophile slash base, right? And it follows traditional SN2 rules. Okay, so looking at this, let's take a reaction that is a basic epoxide ring opening. What we would see is that if we had an epoxide, and we're going to use some stereochemistry here because we're going to need it, um, and we toss in something like sodium methoxide, right? A strong nucleophile, strong base, methanol, and then some heat. What we'd see is we would end up with a product that looks like this. And as a reminder, there's not going to be any stereochemistry on this carbon here on the right because now this one is achiral, right? And the reason we put stereochemistry on the epoxide in general is because this center right here is chiral, and it's going to have to face the same direction as the other bond. Just because it's a triangle, it has to be on a plane. So, thinking about this reaction, why does it add on the right-hand side and not on the left? Well, because there's two different paths we could take, right? Path A would be the addition to the left-hand side, or I guess the right-hand side here, right? Let's say that we had our methoxide hanging out, right? MEO minus, and it decided to do a nucleophilic attack. Where would it attack? Well, it could attack right here and crack open the epoxide, and that would be a pretty stable way of doing it, right? Because you'd end up with your O minus, and then you'd end up with the methoxide being added. Or we could go down path B, right? For path B, we would say that, okay, in this case, what if it attacked the other side? Because technically, the leaving group is the exact same on both sides, right? In this case, the methoxide would attack here and open the epoxide in that direction, right? This would, of course, be an SN2 where you'd invert your stereochemistry and you'd have the O minus right there. Now, these two paths are very different because notice on the path on the left-hand side, this is on a primary carbon, and path B, which is shown here on the right, happens on a secondary carbon. Now, at this point, we should all know what that means, but as a reminder in terms of energy, the SN2 here is completely the same in terms of enthalpy, right? Both reactions end up forming the same bonds and end up with the products in the same level of energy. But the difference is activation energy, right? Because going up pathway A, which is shown here in blue, this was done on a primary carbon. Whereas pathway B, which is shown here in red, was done on a secondary carbon. And that's going to be much higher in energy due to more sterics and the transition state, right? So path A is the better choice. Now, this isn't surprising given the definition that I gave above. It follows traditional SN2 rules. SN2 always wants to go for the path of least resistance in terms of sterics, right? And so what we're saying here is that basic epoxide ring openings always proceed through an SN2 mechanism, right? Which means that they add on the least substituted carbon. So that must mean that our other epoxide ring opening is going to be a little different. And it is, because this one is going to be the complete opposite, right? It's going to be an acidic opening. So for an acidic epoxide ring opening, it actually uses a weak nucleophile alongside a strong acid. But this is where this reaction gets weird, okay? And this is where a lot of the confusion comes in. So pay close attention because this one proceeds through a pseudo SN2. So what does that actually mean? Well, what we're going to see is that in the case of an acidic epoxide ring opening, let's say we took this epoxide and we added H2SO4 as our acid with methanol, right? A weak nucleophile under heat. What we'll see is it will undergo an addition on the secondary carbon this time, but it'll do it to where it actually changes the stereochemistry. So the question is, why does it attack the secondary carbon? Well, looking at this, our mechanism is relatively simple, right? We already know exactly what it's going to do. The first thing is that leveling effect wise, the methanol is the solvent, it's also the weak nucleophile. But if we were to draw it out, it is going to be the one that takes the proton first. It's going to first protonate the epoxide. What this does is it generates this three-membered ring with the protonated alcohol. And this thing is incredibly unstable. Incredibly unstable. And so once this happens, our methanol actually comes in and does an SN2 with this carbon right here. All right. And so this is what ends up doing our backside attack to generate the newly formed wedge product, right? Where some more methanol then comes in and does deprotonation. So it's kind of like a mixture between an SN1 and an SN2. It uses the nucleophile of an SN1, but does an SN2 reaction. But still the question becomes why? And the reason has to do with this structure right here, right? This is very important. So the why here is technically two parts, all right? So the first part of our why is this occurring? Well, if we think about this intermediate, this thing is doing something that's really interesting, right? And it's something that we kind of see with alkenes, but we're going to see it here and it's going to be very important. There are two things that it could do. Let's say it wanted to go through an SN1 mechanism, right? It could leave as a leaving group two different ways. It could go pathway A, right, which would be leaving and forming a secondary carbocation, right? Or it could do the opposite, where it leaves via what we're showing here as arrow B and forms a primary carbocation, right? This is if it wanted to go down SN1. And we would say that A is better than B, right? Because A generates a more stable carbocation. Here's the thing, though. We know it doesn't go through this. What happens instead is the molecule itself recognizes this and it actually elongates the bonds, right? So the bond length changes when you protonate the epoxide. And what it does is it essentially generates this structure where the bond length to the secondary carbon, this is such a weird way to draw it, actually becomes longer in this state and it generates a very large partial positive on that bond, right? Versus on the side of the primary, it's very small. And so what we're seeing is that this right here is causing the secondary carbon to be more electrophilic. So it's doing this without the oxygen actually leaving. At the same time, the reason this SN2 can happen is because also, if we're looking at this structure just in a general sense, right? If we're looking down this bond and we wanted to attack 180 degrees, what would we see? Well, the Newton projection here is actually pretty good for us because essentially the oxygen that's connected to both carbons and this hydrogen right here, we have a lot of space allotted to us. Unlike general Newman projections of these compounds, where we're facing torsional strain from the other carbon, right? This one is eclipsed. And since it's eclipsed, this 180-degree backside attack angle is generally more free, right? It's not going to eclipse with anything. So the angle for backside attack is less sterically hindered due to the eclipsed conformation. So what this adds up to is that you can actually do SN2s on these and perform them with less activation energy than you would a normal compound. And what this boils down to is overall, we see an energy diagram that looks something like this. So this is going to be our reaction progress, our energy. So first, we take something that's relatively normal, right? The epoxide. And upon protonation, we increase its energy by a lot, right? This is another reason that the weak nucleophile strategy works here. Because remember, the reason most weak nucleophiles don't work is because they can't get over the activation energy hump for an SN2. But now we've already got ourselves partially to the activation energy hump, where now we're going to split into two paths, one where we're going on the primary and one where we're going on the secondary, right? Both of these will end up with the same product in terms of being lower than the starting material because it's much more stable without the ring strain. But the thing is, the secondary goes through it with much less activation energy than the primary because we have this situation where now the secondary carbon is more electrophilic. So it's happier to actually take this and run through the activation energy than the primary. So this is just a lower activation energy than normal. And because of that, acid catalyzed epoxide ring openings always proceed via a pseudo SN2 reaction on the most substituted side of the epoxide. And of note, it can do tertiary, which is the exception to everything we've talked about with SN2. Okay? The other thing to keep in mind is it doesn't have to be sulfuric acid. So let's say you took a very similar reaction, but you use something like HCl and water under heat. What you would see is that at first, the HCl and water are going to react to make the H3O plus. That is expected, right? And what will happen is the H3O plus will then come in contact with the epoxide to protonate it. But then from here, the best nucleophile we have in solution to do the substitution would actually be the chloride. And so then it could come around to do the SN2, and the actual product of our reaction would be the chlorine on that position instead of something like an alcohol. All right. So overall, for epoxide ring openings, here's going to be our very simple summary. For a basic opening, right, what'll happen is you'll have your base, usually with a negative charge. It's going to come in and it's going to attack the least substituted side. Versus an acidic opening, you're going to form this intermediate with the positively charged oxygen because it's protonated, and then it's usually some type of um, conjugate acid of a base that's going to come in, act as a nucleophile on the most substituted side. But since both go through an SN2 like pathway, both invert stereochemistry. And so that there is the final piece of information that you will need on your exam. So this lecture is the last one until exam two, so be sure to make sure you study up on everything that we've talked about. All of this will be on your second exam. And with that being said, I will see you for the next lecture after exam two, where we're going to move on and start talking about some different reactions rather than the same ones over and over again with different variations. I'll see you then.